Hello everyone, then welcome back to my YouTube channel. So we have already completed 2 lectures in this lecture series Discrete Mathematics. So Discrete Mathematics, this lecture series mainly designed for the computer science engineering BTech students. So in this lecture 3 we are going to discuss the topic called Linear Homogeneous Recurrence Relation. So this kind of recurrence relations is very much useful for your future. So first of all, what is recurrence relation? So a recurrence relation is a functional, you can say functional relation between two variables. One is independent variable, suppose we are denoting x, and one is dependent variable on the independent variable x, which is called suppose f of x, and the differences of the various order of this function. So this is the relation between the independent variable, dependent variable, and differences of various order of the variable fx. So the recurrence relation has another name also. We can call it as a difference equation. Like it's not a differential equation, it is a difference equation. And we'll use these two terms anywhere. So it interchangeably you can use difference equation also, and you can use recurrence relation also. So if you see the examples of recurrence relations, so this is another one example of recurrence relation. So you can see this x is the independent variable, f is the dependent variable, and this is the order, various order of the function. This is third order, second order, first order, like that. So these are the orders. So involving the orders, differences, actually the differences of the various orders, and the functions and the variable we are using in the relation. So this is a recurrence relation. This can be written as in different forms. You can use f function, you can use this kind of concept ar plus 3. Instead of a you can use y, instead of r you can use k, you can use n. Any kind of variables or parameters you can use for denoting this kind of relations. Okay, so what is the order of recurrence relation? So if you see that any relation that can be represented, as I already discussed, it can be represented using f ar yk. Instead of a y you can use any other variable, instead of rk you can use any other parameter, that's upon you. So the order of the recurrence relation, or you can say difference equation, is defined is the difference between the highest order subscript and the lowest subscript. If it is in the form of ar or yk, if you see the subscript, so the highest subscripts if you take and the lowest, and if you find the difference between this can be called order. So if you see the example 1, so here the subscript is r minus 1. So the highest is r, the lowest is r minus 1. The difference is nothing but 1. So the order is 1. That's why it is called first order. If we see the second example, the subscript of the variable is k plus 3. This is the highest. This is the lowest k. Difference is 3. K plus 3 minus k, which is 3. So this is the third order relation. It is a third order relation, recurrence relation. So this is called order. And what is the degree? Degree is that if the highest power of the variable fx or ar or yk, highest power, not subscript, that is called degree. If you see this example, here we are using this order is k plus 3 minus k is 3, but the highest power of y variables is 3. So that's why the degree also 3 here. Here the order is r, and it should be here only, sorry, subscript r minus 3. So the order is 3, but the highest power of the ar is 4, so degree is 4. Clear? So this is called degree of a recurrence relation. But at the beginning of this lecture, I have discussed the topic is linear homogeneous recurrence relation. So we'll discuss about this, what is linear, right, and what is homogeneous recurrence relation, because mainly largely you are going to use this linear homogeneous recurrence relation. So as I discussed, the degree is the highest power of the variable. Here if you use y, k or ar or yn anything, or f variable, so the highest power is called degree. Now if the highest power of highest power of the variable is 1, that means the degree is 1, then this kind of recurrence relation is will be called linear recurrence relation. Please remember, what is linear? If the degree is 1, that means the highest power here is 1, right? Now if you see, this is the general form of linear recurrence relation. So first coefficient c0, c1, c2, these all are constant coefficients, these are the variables, this is the suffix, and in the right hand side any variable function of independent variable. Here we are taking n, so Rn. Now if this Rn is nothing but 0, suppose, then it will be called a homogeneous linear recurrence relation. So as I discussed, this will be a linear because the power is 1 and the right hand side Rn is 0. So this is complete one example of linear homogeneous recurrence relation. You can say recurrence relation RR of order 3. Why is order 3? Because R plus 3 is the highest subscript, R is the lower subscript, the difference is 3, so it is third order. Degree is 1 because the power is highest power is 1 here, so that's the degree 1, that's why it is called linear. Right hand side is 0, that's why it is called homogeneous. So whenever you will see one kind of recurrence relation where the degree means highest power of the variables is 1 and the right hand side is 0, that is called a linear homogeneous recurrence relation. So mainly this will be the linear homogeneous difference equations or recurrence relation form. C naught yn plus r, instead of y you can use a, b, any other variable, please remember, and instead of n we can use k or something, any parameter, so don't be confused with this. And this all c naught, c1, c3, these are the constant coefficients. Clear? So these are the definition of linear recurrence relations with constant coefficients. Okay, now coming to the solutions of the form, solution of the equation, solution of the relation. So the solution of the equation of the form which I have already discussed, the form was, please remember, c naught yn plus r plus c1 y1 will be always like that, it will be continue, cn yn equal to 0. So now the solution of this kind of equations will be a form. This is the form of the solution, a alpha to the power k. Suppose this is k, instead of n we are using k. So a alpha to the power k, where alpha is the characteristics root, please remember, and capital is the constant. Okay, so this will be a form of the solution. If we substitute this solution in that form, so you can see this is replaced, all the replaced power will be 1 less. So after simplifying we will get this. So this is the solution form. So this is called characteristics equation, the previous equations, and if we find the root of this characteristics equation of the recurrence relation, so suppose alpha 1 is the one root, so one solutions can be homogeneous solution which will be called a, alpha 1 is the root, so alpha 1 power k. Clear? So this kind of solution form we have in the linear homogeneous recurrence relation. Now to find the solutions, of the linear homogeneous difference equations or recurrence relations, we have total 4 cases. So we will discuss one by one each case. Please give your attention. So the very first case is that if the characteristics equation, which I have already discussed, if the characteristics equation having total n root and all the n roots are distinct, then if the distinct roots are and real also, then the roots, suppose alpha 1, alpha 2, alpha n, all the n distinct real roots, then the solutions will be alpha 1 to the power k, alpha 2 to the power k, all these things. So finally the solutions will be the combination of this kind of things. So the final solutions will be of the homogeneous is this one, yk a1 alpha to the power k, where a1, a2 and an, these all are constants. Alpha 1, alpha 2, alpha n are the roots of the characteristics equation, and this k is any integer value. This is the first case where the characteristics equation has n different root and all are real. So we'll discuss all the cases with an example also. Now the second case is that the roots are real, but it has repeated real roots, not all are distinct. Okay, now for example, if its equation is 2 degrees, suppose you are getting, and all two roots are same, so the equation solution will be this one. Please remember a1 plus a2k into the root whichever same, alpha and alpha is same, so you can write alpha 1 to the power k or alpha to the power k, anything. This will be a solution. If it is 3 degree characteristics equation, suppose this is 3 degree, so it has 3 roots, and suppose all these 3 roots alpha and alpha to alpha 3 are the same, repeated, then the roots, the solutions yk, it can be written as yk. If it is y, if it is a, then ak. If it is anything else, then that you can write. So here yk or ak, it will be a1 a2k plus a3k square, because it is 3, so one term again added, into the root whichever is you are getting repeated root to the power k. Remember a1 a2 a3 all are constant, you have to mention in the solution that a1 capital a1 capital a2 capital a3. You can write c0 c1 c2 also, it's your choice, any constant you can write. These all are constant, you have to mention in the answer. So the final, if you to have repeated roots n times, it will be a1 a2 k square, then k cube, then k power 4. That will be repeated, similar process you can follow, and you can find the solution. So if it is 4, then it will be a1 fourth order, fourth degree equations. If you are getting a1 a2 k a3 k square plus a4 k cube, then the root whatever which is the repeated root power k. This will be the solution. This is the second case. Now the third case is that imaginary root, that means complex conjugate root, not real. If the characteristics having not real roots, complex conjugate roots, alpha plus I beta and alpha minus I beta, or where alpha betas are real, you know that. In that case, the solution form will be this one. Please remember yk, or you can say ak, whatever your form is given. The first root alpha plus I beta power k into a one constant a1 or c1 you can write. Then the second complex root alpha minus I beta power k into the second constant a2, where please remember a1 a2 are all the constants. Clear? And the roots of the characteristics equations you are getting, suppose it's a 2 degree I am asking, so one root is alpha plus I beta, one is alpha minus I beta. This is a 2 degree characteristics equation, suppose, then it will follow this one. Okay, so this is the third case, and this is the fourth case, where imaginary root but repeated, that means alpha plus I beta also repeated, alpha minus I beta also repeated, then it will follow this thing yk or ak, c1 plus c2k into that first repeated root power k, plus you know that if alpha plus I beta is a root of equation, then the conjugate alpha minus I beta also must be a root of this. So this, suppose this is also repeated, so second thing is another constant c3 c4, you can use a1 a2 a3 a4 also, I have already discussed, into alpha minus I beta power k. So if you see one example, so this is suppose one example which is uh, given. So you can see in this example, if you solve it, so first of all you have to see one thing, that what is the order of this. So the highest subscript is r, the lowest subscripts are r minus 2, so the order is 2 of the difference equation, or the recurrence relation order is 2, because the difference between highest and lowest subscript is 2. So you can remember this. So if the order of the equation is 2, so then definitely you will get the characteristics equation of 2 degree. Please remember. So if you write the characteristics equation here, which will be definitely second degree. Why? Because the order of the difference equation is 2. So how to write this? Suppose I am writing in terms of r, because it is r given. So r square minus the coefficient is minus 3 r plus the second coefficient is 2 equal to 0. So second degree equation, r square, r the constant, the coefficients are here is 1, so 1 minus 3 minus 3 2 2. So finally you are getting, this is the characteristics equation, r square minus 3r plus 2 equal to 0. Now this is second degree equation. If you solve it, you will get two roots. Now let's solve it. So if we solve it, what you will get? If you factorize the middle term, you will get minus 2r minus r plus 2 equal to 0. From the first two you are getting r common, so r minus 2. From here minus 1 common, r minus 2 equal to 0. So one factor is r minus 2, another factor is r minus 1 equal to 0. So if you write the descending order formulas, values of r roots 1 and 2. So easily you can see alpha 1 is 1, alpha 2 is 2, both are real 100% and distinct also. So if both roots or any roots, if it's second degree then 2, if third degree equation then 3 roots, if all are real and distinct, then it is the under case 1. Yes or no? So if it is case 1, so what was the solution form? So here we can write the solution form in terms of ak, because here the equation is given in terms of a. So the solution form is ak is nothing but, remember, first constant 1 a1, you can say c1 also, into alpha 1 power k, second constant a2, you can say c2 also, alpha 2 power k. So nothing but you can see a1 1 power k plus a2 2 power k. Please remember, don't forget to write where a1 and a2 are constants and k is any integer. So this is the important to write. So this is the solution form of this recurrence relation. So if we change the value of k, suppose k is 1, so one answer will be, one solution will be a1 plus 2a2. If k is 2, one answer will be a1 plus 4a2. If k is 3, one answer can be a1 plus 3 2 power 3 8a2. So these are the many recurrent solutions for this recurrence relations you will get. So this will be example under the case 1. Right? Now similar process. Now this is the second example I am taking. So again please see this thing. So here the highest subscript is this one, k plus 2, here is k. So the order is k plus 2 minus k, so the difference is 2. That means the characteristics equations you will get second degree, right? So if we write the characteristics equation, so here we are the subscript are given in terms of k, so we write the characteristics equation in terms of k only, which will be nothing but k square, because second degree, minus the coefficient is 6, then k, plus the coefficient is nothing but 1 equal to 0, right? So if we solve this again, so you cannot factorize it using 1, so you can use the formula minus b plus minus something. So if you see easily, you can see that this is nothing but k minus 3k minus 1 whole square, 3k square, sorry, the 9 is there, I am sorry, 9 is there. So this is nothing but 3k minus 1 whole square. 3 square is 9k square, so a square minus 2 into 3k minus, so 6k plus 1 square is 1. So this is on specific form of this, so equal to 0. So definitely it has two terms, one is 3k minus 1, again the repeating term. So you can easily see that the value of k you are getting, one is 1 by 3, another also 1 by 3, because two same kind of not same kind of, exactly same, what is called, factors you are getting. So the k value also will get repeated, and you can easily see this 1 by 3 is nothing but a real number, so real and same repeated, right? So here the solution, or you can say, sorry, not solution, the roots of the characteristics equations of this recurrence relation or the difference equation are real and repeated, and what is the value? 1 by 3. So here definitely alpha 1 and alpha 2 both are 1 by 3, so it is under case 2. What was the case 2? Case 2 is that the difference, sorry, the roots of the characteristic equation of the difference equation are real and repeated, then the formula or the form, you can say the form, solution form. So please remember one thing here. Previous example was given in terms of a, here in terms of y, so we will write in terms of y. But the actual form was given in terms of k, but already k is given, so we will use not k, we will use a n or r something. So here we will write n for example. So the formula is n, then a constant a1 plus a2 n, then the value of alpha 1 or alpha 2 whatever, actually because this is same, power n. We are not using k here because k is already there. So this is the form. So the actual form is a1 plus a2n, alpha 1 and alpha 2 same value, which is 1 by 3 power n, where again a1 a2 constants, n any integer. So this is the case 2. So what is the case 2? If the roots of the characteristic equation are real values and repeated, then this is the case. So it is 2-degree equation. Why it is 2-degree equation, characteristic equation? Because the order of the given problem is 2. If the order of the given problem is 3, then the characteristic equation will be 3. Then if the repeated roots are also, you will get 3 types of repeated, 3 times repeated value, then the solutions will be now a1 to a1 plus a2n plus a3n square, one term will be added. Please remember this thing. Okay. Now coming to the example 3. So here this is the given again. So you can see k plus 4 is the highest subscript minus k is the lowest subscript. So the order of the recurrence relation is 4. So the characteristics equations we will get 4th order. So we start with r power 4. So don't write r here because it is given k, so please instead of r you can write k, because but I have written here as r, but you can write it as k. So r power 4 minus, sorry, it will be plus, it will be plus 4 is the constant, then again coefficient, then again plus 8 is the coefficient, and power will be r4, r3, r2, r0. Cos coefficients are 1, 4, 8 plus 8 plus 8 plus 4. So 1, 4 plus 8 plus 8 plus 4 equal to 0. This will be the characteristics equation of 4th order. Why it is 4th degree? Why it is 4th degree? Because the order of the difference equation is 4. Now what we will do? Now we will do that. We will solve this characteristics equation. We will find the roots. So you can see that it is a again the formula based r square plus 2r plus 2 whole square. If you see, this is the actual formula for this term. Now again twice you are getting this, what is called factor, power square, so twice. So if you solve the one time, it will give you the solution minus 1 plus minus I. As it has twice 2 degree, so it will give you twice the repeated complex conjugate value minus 1 plus minus I minus 1 plus minus I. So definitely it is coming under case 4. So I have not discussed here case 3. You can take any example for case 3, or later we will discuss about case 3 also. So here it is under case 4. What is case 4? Complex conjugate root and repeated. So if you see, if you compare it, you will getting alpha plus minus I beta twice. So alpha is nothing but minus 1 here, beta is nothing but plus 1 here. You see, minus 1 plus 1. Now what is the formula? What is the formula? Formula was a1 plus a2 k, you can use c1 c2 also, into alpha 1, or you can say alpha plus I beta power k, plus different constant a3 plus a4 k, then second conjugate alpha minus I beta power k. So you see, this is you are getting. So here alpha plus I beta is minus 1 plus I, here alpha minus I beta is minus 1 minus I. So this will be the form. Again a1, a2, a3, a4 all are constants, k is any integer. Clear? So please remember, so these are the 4 cases you have. First case, please remember, first case is if you have the characteristics equation and you are getting different real root, real and distinct, then the form will be different. What will be the form? In that case, the form will be, is very simple. In that case, form will be a1 alpha 1 power k, a2 alpha 2 power k. Alpha and alpha are different values. If it is 3, it has 3 roots, 3 degree equation, then one more will be added, alpha 3 power k. It will be continue like that. Now, second case. Second case is that real roots but repeated. Now, suppose it is 2 degree and repeated, alpha and alpha 2 both are same and 2 degree, so it will be a1 plus a2k into alpha 1 or alpha 2, same value, so there will be no change, power k. Now, if it is 3 degree, if you have alpha 3 also same, then one more terms you have to add. If it is 4, then you have to add a4k power 3. So, this is the case where roots are real but are repeated. Okay. Now, third case is that complex conjugate. Suppose it is 2 degree equations and you have two complex conjugate root, one is alpha plus I beta, one is alpha minus I beta, two complex conjugate root. Then in that case it will be a1, then first conjugate alpha minus I2 power k, I beta power k, plus a2 alpha minus I beta power k. And the third case I have already discussed, sorry, fourth case I have already discussed here, that complex conjugate but repeated. That means alpha plus I beta also twice there, alpha minus I beta also twice there. So definitely it should be 4th degree minimum of the characteristic equation to use the case 4. So these are the 4 different cases to solve a linear homogeneous recurrence relation or difference equation. So please remember one thing, find the order of the difference equation. How to check the order? See the difference between the highest subscript and the lowest subscript. This will be order, and the degree of the characteristics equation also will be always the same as the order of the difference equation. And how to write the characteristics equation? Suppose the degree is 2, so start with r power 2. If 3, then start with r3. If 4, then start with r power 4, and just follow the coefficients. So start with r power 4, then r cube, then r square, then r power 0. Similar way, just put the coefficients from the difference equations. So you will get the characteristics equation. So if you get the characteristics equation, solve it to get the roots, then check the roots are under which case, case 1, case 2, case 3, case 4. Then you just use the same form of the solution of the according to the case. Now question is that here a1 a2, in the every case you are getting constants, capital A1 a2, right? Some for first 2-3 cases you can get a1 a2 a3 also, and in the last case you can minimum you will get up to a4. Now question is that these are the constant, so can we find the constant values? Yes, we can find, but this kind of problem should have one initial condition. So we can find the particular solution by finding the constant values. In that case, initial condition must be given. So if you see one example here, so this kind of solutions are called particular solution. Previous all examples were the solution form which was given general solution, but here we can find particular solution by finding the capital A, capital A2, A1, these values. Please remember, capital A, capital A2, these values we can find, and we can put the specific value using this kind of initial conditions. This is called initial conditions. So we are going to solve it by quick. See, so from this you can see r and r minus 2, so the difference is 2, so degree of characteristics equation will be 2, so r square is starting, then minus 4 is the coefficient, then r, then plus 4 is the coefficient, equal to 0. If you solve it, you will get r minus 2 whole square equal to 0. If you solve it, you will get r values twice 2, because same factor is repeated. So it is the real, so alpha 1 is 2 and alpha 2 also 2, both are real and repeated. Simple. So definitely the solution AK, you are going to get A1 plus A2K into alpha 1 power k, which is nothing but 2 power k. Here alpha 1 is 2. So this is the solution. Now we have some condition. What is the condition given? Please see that condition. A naught is given 1, A1 is given 6. So to get A naught, you have to put k equal to 0. So if you put k equal to 0, you will get A naught equal to k0 means this term is 0. So only A1. 2 power 0 means 1. So A1 is A naught. A naught value is given 1. So finally capital 1 you are getting 1. Simple calculation. Next, to get A1, put k equal to 1. So if k equal to 1, you will get small a1. So capital A1 plus k is 1 means A2. 2 power k means only 2. A2 value already, A1 value already calculated. So small a1 equal to 1 plus A2 into 2. So if A1 is given 6, so 6 equal to 2A1 plus 2. So definitely A2 plus 2. So definitely A2 is nothing but 2, 4 minus by 2. So capital A1, capital A2 value we got, just substitute here. So the particular solutions you are getting AK equal to capital A1 is 1, capital A2 is 2 into k, 2 power k. This is the solution. Okay, so this is the concept called linear homogeneous recurrence relation, or you can say difference equations. Okay, so thank you for watching me. So that's all for in this lecture. So in the next lecture we will again come with a new topic in the discrete mathematics course. Thank you.